Log on, tune in, find out. Another good idea from Cambridge.
To speak here. So, can you hear me? Well, very good. So I want to talk about solutions of the heat equation on a really arbitrary metric graph, and by properties I mean the validity of a parabolic Harnack inequality. And to do so, I once again, at the end of this conference, try to define what a metric graph is, but I try to be short in this thing. So I start with definitions. So metric graph, as usual, we have a vertex set V, and we have an edge set E, and we, as usual, identify elements of the vertex set with an edge, with an interval of length LE, where LE is a function defined on the vertex set into the positive numbers, real numbers, and we glue those intervals together according our graph structure, right? And so just to show you one graph, but in general I'm interested, or yeah, more interested in infinite graphs. So just think of the vertex set and the edge set to be infinite. So and on the graph we define the a metric for different points of the graph. We can we know what paths are, so we can connect both points via a path. We know how to measure the length between the length of a path, and then we set the metric as the infimum over all paths connecting x and y of the length of those paths. And as we, or as I want to assume that it is connected, it gives the metric on the graph. Moreover, just to fix notation, just to fix notation, given a compact subset of the graph, we set the integral over a function defined of the on the graph by integral y u of x dm as the sum over all edge, and then we look at all possible intersections of y with the edges and integrate as we know it from the intervals, right? So u e x dx, where x is the usual Lebesgue measure on each interval. So, and this gives them, as we know, for LP spaces, just the direct sum over all LP spaces on the intervals. Okay, and for this talk today, we want to have a look at a kind of special class of metric graphs, namely graphs of bounded geometry, and as in the combinatorial case, we mean that there exists a positive integer which we call the gamma, such that each vertex degree, which I denote by dv, is less or equal to the gamma. So we have a uniform bound from above on the vertex degrees. And secondly, we assume that the length of the edges is uniformly bounded from below by a positive constant. So this makes our metric space nice. Right. So one remark, and this is almost obvious. The metric space defined so under this condition is complete. Okay. So now I want to introduce solutions, weak solutions of the heat equation, and my approach is via quadratic forms, in particular via the theory of strongly local Dirichlet forms, and I should define it now. So we take as domain of our energy form the Sobolev space of order 1 on the graph, which is nothing but all functions u which are continuous on the graph, and the sum over all norms over the first derivatives is finite. Over the square of the derivatives is finite. And the form is the usual, or the rule is the usual energy form, almost the usual energy form. So we sum over all edges, we integrate over the interval u e prime x times v e prime x dx. And I forgot to mention that the function restricted to an edge I denoted by ue, or with the subscriptum ue. And wasn't completely right. I also allow measures aex dx where A is defined on x gamma and is bounded uniformly from below by a positive constant and uniformly from above by a constant. A is measurable and lambda is positive, okay? So, and it's so for those who know what the Dirichlet form is, or the strongly local Dirichlet form, it's not hard to see that this actually defines a regular strongly Dirichlet form. And this is our starting point. So, and now, as I told you, we introduce solutions of the heat equation. And we're interested in very weak or pretty weak solutions, and therefore we consider a Gelfand triple of our Sobolev space, where we know it is continuously embedded into the L2 space. And we dualize this space, if we view it as subspace of L2, we dualize it over the L2 scalar product, and the resulting space we call W minus 1, 2. And now for a real interval, we say that a function u, now I'm sorry about the notation, now I use the same letter for this function. Function u defined on the interval with values in W12 on x gamma is in the parabolic Sobolev space, which I will denote by W x gamma, I times x gamma. If this function is in the L2 space of functions with values in W12 on x gamma, so the integral defined in the sense of Bochner. And secondly, the weak derivative, which is nothing but the usual weak derivative or distributional derivative on each edge of U should be in the L2 of I mapping to W minus 1 to x gamma. So for instance, we allow the derivatives to be in some sense very non-regular, since we know by Sobolev embedding theorem that, for instance, in the space we find the delta function of. Okay? Pardon? Pardon? This is the I don't understand. The time parameter. So use a function of t, right? A function of t with values of in the space. Okay. But from now on, I will use the following notation for u. So u depending on t and depending, of course, on x, where x is in the graph. Okay. So, and we call a function u a weak solution or a local solution of the heat equation on a parabolic cylinder Q, or on a subset Q, which is a interval times a open subset of the graph. If U belongs locally to the parabolic Sobolev space, meaning that on each compact subset of Q, we find a function in W which agrees on Q with U. Okay? So it's W log on Q. And very important, U satisfies the following equation, namely it's kind of a variational equation, the formulation of the heat equation so if this equation is satisfied for all functions v, and for all, first of all, for all relatively compact subintervals of I, and for all test functions V, which means they are also locally in our, they are not just locally in our parabolic Sobolev space, but they vanish, or they somehow on the parabolic boundary of Q. So this would be our U, this is our I, and this would be the Q. So the test function V shall vanish on the parabolic boundary, which is the bottom of the cylinder and the boundary. Okay. And so, with this definition, we can state the Harnack inequality. The Harnack inequality is a priori estimate for solutions of the heat equation, and it looks like the following. There exists an intrinsic constant, CH, just depending on the vertex degree, so or the upper bound of the vertex degree and on the lower bound on the of the edges, such that for all x in x gamma, small radius r, arbitrary s real, and any positive local solutions of the heat equation in the following set, namely so-called parabolic cylinder. So we have the interval from S to S plus R square times the ball around X with radius R. And we have the following estimate. U of T1 X Y1 is less equal than CH times U of T2 Y2 for all T1 Y1 in Q minus, which is so if this is X, this is R, this is R square. This is Q. The Q minus is something like this. So more precisely, it's S plus R square, S plus 4R square times Brx, and all T2 Y2. And this holds uniformly for all pairs in those sets. So Q plus is something like this. And this equivalently can be stated, oh, it's obvious, nice. We can also write this in the usual form of the Harnack inequality. We look at the supremum on Q minus on the left-hand side of the inequality and have this uniform estimate by the infimum on Q plus of U T Y. Not yet. It follows from the Harnack inequality. It's following from the proof. You show at one point that it is continuous. No?
So you prove that the solutions are necessarily continuous jointly.
Okay. Yeah. So you would prove at first that the essential it should be continuous because functions here are continuous in Sobolev
Yes,
space.
in L2 in time, values which are continuous but less.
Okay, in time. Okay, then we have to argue about, first of all, the essential supremum and the essential infimum. And via this, we can prove that the solutions are Hölder continuous. And then we have this pointwise estimate. Okay. So, let me continue with some remarks what makes this so interesting. So first of all, we see from, for instance, this equation that the parabolic Harnack inequality implies a maximum in principle. Since assume that for some late time and for some location of our y, u has the value 0, then it implies that for all times before we the solution is 0. Okay. Secondly, and this was I think due to Aronson and later Solovkost, I think. I don't know, but I will comment on this in a few minutes. The parabolic Harnack inequality is equivalent to heat kernel bounds the following form. It's bounded from below by the following expression. And from above by this expression. So we have Gaussian heat kernel bounds. Okay. Let's see. So we have this those Gaussian bounds where the constants are just depending on the intrinsic geometry of the graph, and the constant in this exponent reflects the local dimension of the graph. Okay, and I really have to say some remarks on the history because almost impossible to comment on the whole history. The method used for the proof was developed by Jürgen Moser in a series of papers, where two of them were dedicated to parabolic problems. So he proved it for uniformly elliptic operators in RD. And some years later, Grigoryan, 90, and sum of cost independently from each other. Proved it for uniformly elliptic operators on Riemannian manifolds. And finally, Karl Theodor Sturm generalized it to the setting of strongly local Dirichlet forms, where our model, where we can apply those methods to our setting. But not just for continuous spaces. The Harnack inequality was proven also for graphs, and there let me mention the works of Del Motte in '99, Barlow and Bass 2004, and also Barlow and Bass and Kumagai in '06. So Del Motte proved it for the combinatorial Laplacian for locally finite combinatorial graphs under some additional assumptions. And Barlow and Bass, they did similar things, where this work is also related to quantum graphs. And this work, there was a Harnack inequality proven for metric measure spaces and Dirichlet forms on them.
But I mean, in the case of combinatorial graphs, you can't possibly get the Gaussian decay. It's different off the angle decay.
Okay, yeah, that's possible. I don't know.
The off-diagonal Gaussian decay depends on the fact that these strongly local.
The upper bound. Ah. And let me finally mention a paper from last year by Bendikov, Salavkost, Salvatori, and Wes, who proved this theorem, or showed the conditions for the theorem for Riemannian complexes, where quantum graph is also a special case of it. Okay, I have 10 minutes left. Yeah, let me just comment the ingredients for the proof which are needed to apply the general version of Sturm. So basically we have to show three things, and the first one is that the following quantity, called the intrinsic metric, defined as follows. Behaves well, and I want to say the following with that. They almost agree, so they are equivalent with the graph metric, depending on our small lambda. So we have this estimate, which is fulfilled in our setting. The second ingredient says that the volume or the measure and the metric behave well. Namely, we have the so-called volume doubling, which means that for all x in x gamma and all small radius r, we have the uniform estimate measure of the ball with radius 2r is bounded from below by a constant times the measure of the ball with radius r, and it's uniform in x and for small r. And the last part is the validity of Poincaré type estimates. So we have the Poincaré inequality which says there exists a constant Cp, also just depending on intrinsical quantities, such that for all x and x gamma small radii and all functions which are in the Sobolev space in this ball we have the integral over u of x minus the mean of u on the ball squared could be estimated from above by the constant times r square times the integral over the ball of the derivative of u squared. So with those three properties we can essentially apply Storm's theorem. Okay, and with these three properties I finish my talk. Thank you very much.